Okay, so our next test is an analysis of variance, or ANOVA. This one compares more than two groups, so nominal or ordinal groups, on some dependent variable that is typically an interval ratio or interval-like ordinal variable. The one that I'm going to use for this, that I always think is kind of fun to use, is the zodiac. So we do have the zodiac signs in the GSS. They're in the 2010 GSS. They're in all of them. So we're going to do a quick illustration just showing, in all likelihood, that there is no relationship here. So first thing I'm going to do is load my EXPSS library. I'm going to use this to pull information about the variables. So variable label. We're going to look at zodiac first, so I'm going to put that in. And it's telling us the respondent's astrological sign, and then we want to make sure that there are more than two, right? So we're going to check the value labels, and of course it's showing us all of them. So we have everybody's astrological signs in there. For our dependent variable, we're using a different one. This one is going to be word sum. Word sum is a count of how many words the participant got correct out of 10. So it's number of words correct in a vocabulary test that they were given. If astrological signs actually matter, then theoretically, again, it's all garbage, it doesn't mean anything, but theoretically, members of certain signs would score higher on a word sum test. They would have, be more knowledgeable or something like that. But of course, it doesn't mean anything. So these are my value labels, and of course it's not going to show us most of the value labels. So if we're looking down here at our output, it's not telling us that if you got 0 correct, you got a 0, because 0 means 0, 1 equals 1, so on all the way up to 10. For our analysis of variance, what you are going to see here is when we run it, at least initially, there won't be output down here. We're going to add the output to our global environment, and then we can interact with that output. So you get to call it whatever you want. I tend to call mine something that reflects the variables involved. So this is zodiac by word sum. Doesn't matter. Again, you can call it however you want. The code is AOV. Your dependent variable goes first. In this case, our dependent variable is word sum. We use this squiggly little line there to indicate it is dependent upon. And this next part is actually really important, particularly if there are statistically significant relationships here. You want to put in your independent variable as a factor variable, right? Just to make sure that R is treating it as a factor variable. And that, of course, is going to be our zodiac. So we plug in zodiac here. And then we can run this. Like I said, no output down here. It's going to store it over here as an object in our environment. So we run this. We can see the object over here, and then we can get a summary of that output, and that is going to tell us whether we have a relationship, statistically significant relationship, between signs of the zodiac and scores on word sum. So we run this, and what we're looking for in particular, so this is degrees of freedom, a whole bunch of things, is the F value right here. That's our F ratio statistic, and the P value. Not surprisingly, our F value is really small. Our P value is above 0.05. There is no relationship whatsoever between your sign of the zodiac and your word sum scores. Just more evidence suggesting that horoscopes are a joke. They might be entertaining. You can, if you want to read them for entertainment value, that's fine, but they don't actually mean anything. It's complete garbage. And you can see it statistically now, which is loads of fun. But I do want to do a second example where there is a difference, so we can show the follow-up test that you should do in order to do kind of a robust analysis of something like this, because if there are differences, you want to find out where they are and then detail where those differences are and what the differences look like. So we're going to do something else where we think there might be differences by on the word sum score. So we'll use the same word sum variable. We're going to change our independent variable to something else. We're going to use degree. So in the GSS, it has their terminal degree as a different variable. So we're going to just put that in. So this is our variable label, and our value label is going to be the same, GSS 2010 degree, and it's going to tell us what the different options are. So we've got less than high school, junior college, bachelor's, and graduate. So we just want to look and see if depending on people's level of education, they score differently on the word sum variable, and then if they do, we want to see where the differences are. So in this case, I'm going to do the same analysis of variance, but this time it's going to be degree by word sum. Again, you can call that whatever you want. Code is going to look very similar, so it's GSS 2010 by word sum, and it is dependent upon as factor. We're going to plug this in, and we're going to put, this time, degree. Okay, so that is going to be our code. We're going to get nothing down here, and up here it's just going to store the output, right? So we're going to store the output, and now we can do a summary of degree by word sum, and I'm guessing we're going to find a difference. Sure enough, we found a difference, right? So what we're looking for again is the F ratio statistic. It's right there, it's quite large, and this is scientific notation saying it's less than 0.05. Again, that's our cutoff, so that's all we need. The tricky part about ANOVA, though, is it doesn't tell us where the differences are. So all it's saying at this point is for all those different degrees, right? So less than high school, junior college, bachelor's, and graduate, there is between them somewhere some statistically significant difference, but it doesn't tell us where the difference is. The follow-up, called a post hoc test, right? The standard one that's in base R is called Tukey's. So we do Tukey's highly significant difference test, and here's the nice thing. You can literally just take the same output. So I'm using the same output, and you do Tukey's on this. This is also an important reason why you have to do the as factor. Tukey requires that your independent variable be a factor variable. So we're going to run Tukey's and see if it'll tell us where the differences actually are, and of course it is. Over here, these are just saying the 1 and 0, those are the codes, right? So if we go back up and look, 0 is less than high school, 1 is high school. So if we look, is there a statistically significant difference between those who didn't finish high school and those who did? Right here, that's our p-value. That is telling us, yes, there is a difference, and this is the actual difference. It's about 1.53 words. Those are the number of words different, right? So we can compare all the zeros. That's what Tukey's doing, is basically all of these tests, right? Probably our biggest gap is going to be that one right there, right? So if we look again, 4 is graduate degree, 0 is less than high school. The number of words different on average is about 3.42. And this, if it's less than 0.05, tells us that it is a statistically significant difference. So we're looking across here, we can see that there are statistically significant differences for most groups, not for this one, right? So 1 versus 2, that's high school versus junior college, not significantly different. And 4 versus 3, I'm guessing that's a bachelor's degree versus a graduate degree. Yeah, not statistically significantly different. So difference, but it's not significant, so not a meaningful difference here. So that would be the next piece, and then what I usually like to do, I use a different package. So I like the psych package for this. I'm going to load the psych package, and what this will allow me to do is very quickly just do a describe by. So I like to use describe by. My dependent variable is going to still be word sum, okay? And we are describing word sum scores by the groups. So we're going to put our groups back in, and this is going to be degree. And what it'll do is basically just list out all of the mean values for all the different groups. So I'm going to just kind of make it so we can see them all. So that's group 0. We can see their mean score on word sum. Here's group 1. That's their mean score. Group 2. There's group 3, and so on. So this is a useful way to see the differences, and we can just get the mean values for all of those. So that is how I would run an ANOVA. First one, not significant, right? Zodiacs don't mean anything. Second one, degree, clearly does mean something useful to do.